Okay, ready? Welcome to EE 123, lecture 17. Woo! I'm excited. Today we're going to talk about lab 3 and polyphase filters, okay? Anybody started lab 3? We just posted it, I guess, so I can understand. How's the homework doing? Everybody good on the one that has a little bit like the wavelet denoising one? It is hard. I completely agree with you. The main purpose of that problem is really that you go through mathematical derivation and see that you can reduce the noise quite a bit using wavelet thresholding. And if you compare that to just low-pass filtering to achieve the same level of noise, you barely touch your signal, whereas if you did low-pass filtering, your signal would look very different than what you started with. So even though you reduced a lot of noise by low-pass filtering, you really also removed a lot of your signal. While with wavelet thresholding, you barely touch the signal, but you remove a significant amount of noise. Okay, so that's what you go through. And you actually calculate how much low-pass filtering you need to achieve to get the same amount of denoising and how crappy your signal is going to look like after you do that. So that's what it's all about. But if you're having trouble, then I would say you should have come to office hours. Right? So how many people have not done that question yet? All right. Due today, right? Tomorrow. Oh yeah, we'll give you one. Okay. All right. Plenty of time. I think it's a really, really neat exercise. And it doesn't really require much probability knowledge, except for the fact that when you look at an expectation of a multiplication between two random variables that are independent, then it's basically the multiplication between the expectation of each one of them. So if you have something that is independent and they're zero mean, then the expectation of their multiplication is also zero mean. And when you have also vectors which are orthogonal, then if you look at the inner product between those two vectors, they're also zero, unless it's the same vector. So it's kind of the same thing. But what it'll come out to be, then you will show that if you have random noise or random Gaussian noise in the signal domain, when you compute the Haar transform, you still get the same random Gaussian noise after. And once you threshold, and you threshold in the way... Oh, thank you so much. I'm going to take a break here with the audio for a second, for those watching online, because we have replacement batteries. Thank you. Oh, yeah, thank you so much. And I'm back. Okay, thank you. Okay, so where was I? Before that. I was done with that? Huh? Oh, wait. So when I threshold, and I get basically noisy coefficients. And so when I reconstruct my signal, it's just the sum, a weighted sum of these, basis function that are weighting the noisy coefficients. And so you just need to calculate what is the standard deviation and mean in the signal domain back. And you'll see that it's much lower. So that's really what the problem is. And good luck with that. All right, so today we're going to talk, last time we talked about changing sampling rate via DSP, upsampling, rational resampling. Today I'm going to talk a little bit about Lab 3. For those who are going to start, you'll have an idea kind of what is this all about. And I want to get you excited about this lab. Then we're going to talk about interchanging compressors and expanders and filtering. We started doing some of this last time. That would lead to what's called a polyphase decomposition, which is just a fancy word of basically breaking a filter in a way such that when we compute the filtering operation followed by decimation, we don't compute things that we're going to throw away afterwards. Okay? So that's a fancy way of describing this particular operation. That will lead to a multi-rate signal processing when we're going to talk next time. And in multi-rate signal processing, if you think about it, it's kind of like a wavelet thing where we filter down sample and then do the operation on a different rate and maybe go and upsample again and so on and so forth. So that's what's multi-rate. And you'll see that will really tie back to all the stuff that we learned about wavelets, and we see from a different point of view what does that mean and how they relate and how things can be reconstructed and so on and so forth. And computed very efficiently. Lab 3. So Lab 3, we call it time frequency, and it's basically about computing time and frequency operations. So you're going to be computing spectrograms. So you're going to write a function that computes the short time Fourier transform and computes a spectrogram in a way that looks nice. And you're going to look at different type of signals. So one of them is this bird chirping audio, where this would be without windowing, that would be with windowing, and you'll see the differences when you go through them. You're going to look what happens when you compute with overlapping window. That gives you a nicer transition over time at the expense of a little bit more computation. So you'll get really kind of a nice, smooth, interpolated signal. Then we're going to look at the trade-offs between temporal frequency and resolution, and temporal and frequency resolution trade-offs. So you're going to look at this ORCA signal and look at different size windows of how you can differentiate between things that are changing really rapidly, but also between different frequencies, and so on and so forth. So this is all just audio and just very simple. That should be relatively simple. The next thing I think is really a cool part of the lab that we introduced last year, where you're going to write an FM radio receiver using Python. But it's not just an FM radio receiver, or actually a broadcast FM radio receiver. You're also going to look at the subcarriers that are being transmitted, that you cannot listen to them normally on a regular radio. You have to have a special radio to listen, but you're going to use your software-defined radio because it's so easy to do things when things are just samples. Okay. So there's our own KPFA FM Berkeley station. It's up on the hill. It's located, if this is campus over here, it's located up here. You could see the antennas if you drive up Claremont to Fish Ranch Road. You'll see some antennas over there. This is KPFA. That's where it's transmitting from. This is the kind of the 30-mile coverage of this station. It has pretty nice coverage across the entire Bay Area. And what you're going to do then is you're going to capture samples around this station, which is 94.1 megahertz, and you're going to acquire a bandwidth of, probably 240 240 kilohertz rate. Okay. Actually, your sampling is going to be much faster, but you're going to get 240 kilohertz of bandwidth. That's what your sampling would come to, and you're going to look at the demodulated spectrogram. So just look at the raw RF, okay, and look what the spectrogram is, and you'll see that it kind of looks like it's frequency modulated, because you see this is a speech, I think. And when you have speech, then it's kind of obvious when it starts and stops. And it's frequency modulated because you see that the information is encoded in the frequency. So the frequency changes over time. Okay, frequency modulation. So you're going to look at a spectrogram over about 8 seconds. Then you're going to FM demodulate it. Okay? So because everything is now in digital form, all you need to look as the change of phase with time. What is frequency? Is the change of phase over time. That the derivative of phase over time. So you're going to approximate a you basically it's really easy to look at the phase because everything is digital now. So you can just look at the phase. Okay, everything is complex and digital, so it's no problem to look at the phase. And what you're going to do is you're going to take derivative of the phase and demodulate the FM signal. Okay, so just by computing finite derivatives by finite differences. Okay, there's a trick that you'll do over there. Basically, do things in the complex domain, but all the instructions tell you how to do this. It goes through the derivation very nicely. But you see how simple it is to build an FM receiver when you're actually writing it in Python as opposed to making a circuit. Okay? The circuit's now done for you. It does a lot of other things, but now you can just take those samples and then do an FM demodulation, even though this chip is meant for something else. So this is the spectrogram of the demodulated signal. What you have here is, let's see, that's the next slide. So it's very different than this one, right? Because this was FM modulated to get that. So the demodulated signal, that's the spectrum, and now I'm showing just a one-sided spectrum. Here I showed a two-sided spectrum. Why? This is complex values, right? The SDR gives you complex values because it represents, only one side part of the spectrum. Remember, we talked about why it does represent this. It represents frequencies from 9.4 megahertz to 9.42 megahertz. So this has to be complex. It's just one side of the spectrum. When you demodulate, this is all real. Okay? Because we also look at the phase. The phase has real values, right? When you actually look at the values of the angle, right? It's real. So it has just a one-sided spectrum. The other side is completely conjugate symmetric to it. So this is, when you look at Wikipedia, of how broadcast FM spectrum looks like, it looks like this. Up to about 16 kilohertz, you have the left plus right mono information. Okay? So that's up to 16 kilohertz. At 19 kilohertz, you've got this pilot signal that is a reference. And all the other information is multiplications, basically harmonic multiplication of this pure tone. So here it's amplitude modulation of the left minus right. You can use this, the double that frequency, to demodulate that and recover it, if you really wanted to. So this is the left plus right, and so what we have here, this is this part, you see? This is the pilot. Because it was... It's always a connector problem. Okay. So because it was mostly voice, there's no audio, there's no stereo in voice really. So this one is almost gone. There's really nothing here. But that's because it was voice. Then at 57 kilohertz, you have got the RBDS, which is the digital information that tells you kind of what's what is channels that you're listening to, and what song is being played sometimes, and so on and so forth. This is this part. And then at 67.65 and at 92 kilohertz, you've got what's called subcarriers. And it turns out there's Punjabi radio and also French Haitian radio that pay KPFA to put some of these stations onto that signal. And there are some radios that you can buy that would play that for you. But you see, these are kind of low bandwidth FM modulation. You see that's FM modulation? It's FM modulation, it's FM modulation. It's kind of like double FM. right? Because this will be FM modulated and transmitted. Once you demodulate, this is still FM modulated. You have to FM demodulate that again in order to recover this. Yeah.
So those sub-carriers, do they contain all these components?
No, they don't have enough bandwidth to do that, right? Of course. No, those would be like 5 kilohertz, 10 kilohertz bandwidth, so it's not high-quality audio, of course. Yeah. And so what you're going to do is first you're going to demodulate the mono part, okay? You're going to demodulate the mono part. So you're going to so there's a couple of things. First of all, we need to when you want to demodulate the mono, the fact that you have samples at 120 kilohertz, or actually 240 kilohertz, so the maximum frequency is 120. Your sound card cannot play that rate. You have to change the rate in digital form, right? And you need to change the rate, but you don't want to get aliasing. So you need to apply a anti-aliasing filter, right? So you're going to apply an anti-aliasing filter at about 16 or 18 kilohertz. And then you're going to downsample by a factor of 5 to get to a rate which is 48 megahertz, which that allow the computer to play. Okay, 48 not megahertz, 48 kilohertz. Sorry about this. Okay, so after that summation, now if you compute the Fourier transform, you'll see that this is what you have. Okay, so it stretched it. Remember exactly what we did. Like low pass filter, downsample, it stretches the frequency. Right, you're going to be able to see this. Okay, and then after that you're going to play it. Okay.
Another Planet Entertainment.
And that's going to...
Did I say Sunday, March 16th at 8 o'clock? Yes. And if you buy a ticket...
Okay, so this was this audio. Okay, 8 seconds of audio. All right, so after you're going to do this and play this, you're going to demodulate the subcarriers and listen to them. Okay? So the subcarriers are up here at 96 kilohertz, right? So what we need to do is we need to demodulate it to 0 frequency, okay, and then low pass filter and again either downsample or just low pass filter. Yeah. So after demodulation, what I did here is a complex demodulation. Complex demodulation basically circularly shifts the spectrum. If you complex demodulate, it circularly shifts the spectrum. So the spectrum that's up here, now it's down here. Okay, so everything shifts down. And now I'm showing the full complex to two-sided spectrum. Now it's centered around this 96 kilohertz, and everything is kind of moved down, and then you see the circular shift of it. Okay? Yes? Then I'm going to filter and decimate. And when I filter and decimate, it looks like this. This is filter and decimate. And now this is FM modulated. So what I need to do again is FM demodulate. In the same procedure that I did for the RF part, now I'm going to do it at this rate. Okay? And when I do that, you're going to listen to this. This is the actual, it's quite noisy, by the way. But you're going to hear it. Okay, so you're going to be able to listen to that station, and then you can listen to the other one. Yep. First of all, I think I captured something that was relatively noisy up in the beginning. The other thing is that when the high frequencies in FM radio are noisier. Okay, there's more noise. It's the fact that I take a derivative operation to demodulate, it amplifies the noise in the high frequencies. So that's what they do actually in FM is that they pre-compensate for some of those. They have a pre-compensation filter that amplify the high frequencies before they FM modulate, and then you have to kind of tone it down after you demodulate. But the problem is here in this case is that it's already high frequency, and it is going to be suffering from noise a little bit more. If I would have probably been outside and acquired that particular data, I might have had a better result. Okay. But it's a little bit more prone to noise. Any questions? So this should be fun. You'll be able to hear something that, and then at the end you're going to do the same thing in real time. Okay, so all the functions that you have, you're going to put in a real-time type of procedure and see the spectrograms and also play the music in real time. So basically have a radio that can play subcarriers. If you're into Haitian, French Haitian or Punjabi radio. But I think it's nice to see something that you cannot see otherwise. But it's there. Okay. Ready? So the idea there is that in this whole lab is that you learn a little bit about the spectrogram and time-frequency decomposition and see those trade-offs. Then do some of this decimation operation, FM, learn a little about actually how broadcast FM works, and do things that are actually real samples that you capture from the waves, from the airwaves. Okay, so last time we talked about the interesting case or the curious case of, yeah, great, I want to resample, but what if I want to resample only by 1.01? Okay? And we saw that it would be really expensive to do it the way that we were thinking. For example, expanding by a factor of 100, which is really computationally intensive. You have, there's lots of memory. You need to use really large filters. And then you're going to downsample everything and throw a lot of those samples away, which doesn't make sense. Right? So, fortunately, there's a way around it, and that's what we're going to talk about today. So I started talking about how to interchange operations. So if you have an expander and compressors, okay, if you have a filter followed by an expander and an expander followed by a filter, we saw that these are not equivalent, but you can change this filter to make them equivalent. Okay? So we went through the math and showed you that, in fact, if you change this filter instead of h of z to be h of z to the power of L, basically you upsample it, right? You put zeros between the taps of this filter. This is basically what it means to expand it. Okay? If you expand the filter, then that will be equivalent. Okay? So that's great. And the question was, okay, so you could do this, but what if you have an expander followed by a filter? Can you then replace those? So it's the opposite way. Okay, not having this and going from here. How about from here to here? And turns out that it is possible to do this as long as this is rational. Okay? I think this is a mistake, which should be h of z to the power of 1 over L should be rational. Okay? Or 1 over L, right? That should be rational. And if that's true, that's great. And I showed you an example when it's not true, what happens, right? With that it has to be a result of an expander. Whatever comes out of this filter, whatever comes out of, here at this point has to, what do I want to say? Anyway, I lost my train of thought. But if you want to replace, then you want to make sure that whatever comes out of here is also a result of an expander. Otherwise, it's not possible. Okay? So if this is not a result of an expander over here, then you cannot do this. Okay? Because if I replace it, there's an expander here. Of course, you cannot replace it. That was my point. So now the question is, what happens with a compressor? Folks in the back. What happens with a compressor? With a compressor, we want to see whether we can exchange those. And as it turns out that it is possible, if you have first a compressor followed by a filter, it is equivalent to exchanging them, but now you need to expand the filter. Because what you're going to do then is going to decimate it. Right? So if you expand it, then it actually works. So the way we're going to show it is that it actually works is I'm going to define V of n to be this point, and I'm going to go through and derive what is yn in the frequency domain. And then I'm going to show you that if I take V of n and I push it through a compressor, it's going to look exactly the same as this. Okay, this is kind of the way I'm going to solve it. Okay, find an expression for y of n, and then show you that V of n pushed through a compressor looks exactly the same. Okay? So if I look at why y of n is, right, y of n is the result of compressing and then filtering. Okay? So this is the filtering operation in the frequency domain multiplied by the compressing. What is the compressing? Is stretching the frequency and then replicating it, right? Okay, so this is, we derived it before, right? This is the stretching, and this is the moving it by m times. So what I'm going to do now is I'm going to take h e to the j omega and move it inside the sum. Okay? I'm going to move it inside the sum. That's not a problem because it's not even a function of I. But I'm going to make it into a function of I in a way that doesn't change it. So I moved it over here, and basically it is shifted by 2 pi I. 2 pi I doesn't do anything because h of z is already periodic with 2 pi. Okay, so it doesn't matter. So this is exactly h of z e to the j omega. It only looks like this. And the reason that I made it look like this is because I want it to look like this. It still doesn't look exactly like this. So there's an m here and there's no m's here, so I'm going to just multiply by m and divide by m. Okay? So I multiplied by m and divided by m. Now they look the same. Okay? All right. So what is v? V e to the j omega, right? V e to the j omega was the expanded filter multiplied by x e to the j omega before. I'm going to go back and show you. If I push that in through a compressor, okay? If I push that into a compressor, this is exactly what I'm going to get. Okay? I'm going to get a stretching by m and replication. And this is exactly what is this described. Okay? QED. So if that was V of n, which is basically the just filtering with a compressed version of h z to j omega, then after this compression, it's going to look exactly like this. And this is the result. So now the question is, can I move the compressor from right to left? So the opposite. If it's on the right, can I move it left? And what's the answer? So what if the compressor was over here? Can I replace them? Can I switch? If that was my situation, I have h of z, and then followed by a compressor. Can I switch it into this? How? Always? Again, when h of z to 1 over m is rational. Okay, that's only the case. Okay. All right. So now that we're equipped, a set of tools of flipping these filters and expanders and all this stuff. Now we're ready to go. Okay? So pay attention. These are equivalent. Okay? I can replace h of z with this and z to the power of l, and I can go backwards, and I can do this and go backwards. Right? Great. The problem is that most filters that I'm going to have don't have the nice feature that if I exchange, then they're going to be rational. That's not going to happen. Okay, most filters, that's not the case. So what I'm going to do now is I'm going to take a filter and I'm going to decompose it into several other filters. Let me argue that any impulse response, okay, any impulse response, I can decompose it into the sum of other impulse responses that are shifted versions of it, of other filters. So here's what I'm going to decompose it to. I'm going to take h of n, and I'm going to break it into these two filters. Okay, I'm just going to look for the case when it's 2. If h of n, I'm going to take the even series, and I'm going to call it h0 then. And I'm going to take the odd series, and I'm going to call the shifted version by 1. Okay? So take these odd series and then shift it by 1 backwards. I'm going to call that h1 of n. Okay, so the blues aligned back to 0 are going to look so I'm going to break this into these two in a way that if this is h of 0 and this is h1 n minus 1 like this, if you add them together, that will give you h of n. Okay? So h1 is you shift left, left, so that if you add them when it's shifted right, then it adds back. Okay? But I want them to start at 0. I want those filters to start at 0. Now, think why I'm doing this, right? Now, how does it look? It looks like a result of a expander. It looks like a result of an expander. Now, I decompose this something that doesn't have, or something that looks like an expander, into two filters that look like a result of an expander. Only one of them is delayed. Do you see where I'm starting to go through? There's this delay. There's an expander. If we're going to decimate, maybe we can do some interchanging. Okay. All right. So what I'm going to define now is another filter, which is the compressed version of these h's. Okay. So if I have all these h's of k, I'm going to decimate them by a factor of m. Those I'm going to call E sub k. Those are just without the zeros. Okay? Those are just without the zeros. So E sub k, if you expand them, then you would get h of k. Right? Or if you decimate h of k by a factor of m, you'll get E sub k. Yes? There's m of these e's. Yeah. There's m of these e's. Exactly. All right, so now it looks like this. This is h0, this is h1, this is e0, and this is e1. Okay? Those are the compressed versions. Now, of course, I can reconstruct back my impulse response by expanding this one, delaying it, and adding it. Okay? This is how I reconstruct it back. The way I got to this is I advance this, separate them, advance this one, and then decimate it. Okay? This is how I got to this. Okay, so now it's getting interesting. Okay? So now I have this case where I can get from E to K by upsampling by a factor of m to h of k. Okay? Also, I want you to recall that upsampling is in fact scaling of the frequency response. So if I upsample in the frequency domain, if I upsample in the time domain, in the frequency domain, it's going to look like capital E sub k, z to the power of m. Okay? That will be equivalent to hk of z. So each one of these individual, part filters, now I can express them as the e's that are, expanded, or scaled. Now, how do I get from all these h of k's to h sub k to h, right? In the time domain, I just need to sum the delayed versions of them, right? In the frequency domain, I just need to sum all those EKs to the z to the power of m and apply z to minus k, which is effectively a delay. Right? Z to minus k in the z transform is actually a delay. So this is transformed into that. Okay? Now what I'm going to do is I'm going to write it as a flow diagram. The same operation now as filtering with h of z, I can do this polyphase decomposition by taking x of n and then filtering with E0 z to the power of m, then delaying it by one sample and then filtering with E1 z to the power of m, delaying by a sample and so on and so forth, and filtering by EM minus 1. Okay? And then add the result. Okay? So all of this is equivalent to h of z, just from this formulation. Okay? I mean, think about it. Like samples come in, right? What are all these E sub k's, right? These are decimated, delayed, part versions of the original filter. So this is basically just breaking it into these kind of form. Okay? So linear combination, if you think of the filter. You're just writing the filter differently. But I'm writing it in a way that will allow me to compute things faster if I'm going to decimate afterwards. If I didn't decimate, this didn't do anything. It's exactly the same as really doing the full convolution. Okay? With this. This is just different reordering of things. Okay, so now the problem is that if I have a system which x of n goes to h of z, and then I'm downsampled, right, and getting w of n, this is really downsampled version of y, which is the result of the filtering. So again, my argument is that I filtered something, I computed something, and I throw it away. I shouldn't be computing it at all. Right? Then I would save computation. So let's see how we're going to do this. So for an FIR filter, I've got n multiplications per unit time. Every unit time, I multiply and add. Right? And my filter is length n. I do n multiplication and then n addition. Multiply and add. Multiply and add. N multiplication per unit time. Okay. Let's see if we can save this. So the question, can we interchange these? And we see that we couldn't interchange this in general case. But maybe there's something we could do. If we do this polyphase decomposition, and now we have y of n here, and then downsample, what we could do is move the downsampling over here before the summing. Before the summation. Okay, that's still linear, right? That doesn't matter. So I'm going to move the downsampling before the summation. Now, look what happens. Now, I can interchange these. Because when I interchange these are going to be rational. Right? If I basically divide by m. So these are going to be rational. So what I could do is interchange these and effectively filter with a smaller filter. And then shift, filter with another smaller filter. Delay, downsample, filter with another filter. When I do that, if I told you actually to implement a filtering downsampling, and you would have, tried to do it fast, and you thought a little bit about it, in your code you would probably skip some operations because you're not going to be computing them. This is what formally makes you do this, by formally thinking about it. You could have discovered, this polyphase decomposition by yourself. But this is a very general framework, right? So probably if you didn't really think about what the structure of it would be, then you would have to do that over and over again. But this is a formal way of, if you have a certain decimation at the end, this is how you should be decomposing your filters and delaying it and running it through the filters and adding them at the end. That will give you the right result. Okay? Fantastic way. Now, the cool thing about this is that I did this decimation over here. But look at this. I mean, this is, you delay by one decimate, delay by one decimate, delay by one decimate. I mean, it kind of makes sense, right? Because there's something that you're not going to be computing. And when you delay, you still have all the translations. Okay, so now let's do the calculation of the operations. So each filter has n over m times of operations per 1 over m, n times m, n over m times of operation, right? Because we have n filters, right? Each one of them let's see. Each one of these is 1 over m type of multiplication, right? So it's n over m. This is n over m type of multiplication, right? Because we downsample. These filters are smaller by a factor of m. Okay, if our original filter was n size, these are size n over m. Okay, we have n over m, and the rate that we do this per unit time, okay, is 1 over m, because the rates that we're computing those are 1 over m. Okay, things are not going as fast over there. Okay, because that's the rate after sampling over here. And then we've got m of these. So you multiply by m, you've got n over m multiplication per unit time overall. Okay? So this is significant saving in terms of number of operations that you have to apply. Okay. Any questions? Yeah, how do you calculate? Okay, so in the original case, you had n operations per unit time, right? Filters coming, samples coming at a certain rate, and your processor, for a particular time, for unit time, needs to compute n multiplication, right? Multiply and add. Multiplications are more expensive, so we just count multiplications. In this case, let's count. Okay. Each filter is size n over m. Okay. What is the rate per unit time that each filter gets? The rate of samples that come in per unit time. It's 1 over m, because we decimated. This filter's kind of waiting, because nothing comes in for m time points, because it's decimating. Samples coming in, but nothing comes to this filter. So you don't need to compute this, right? Okay. And how many filters do you need? M. So n over m multiplied by 1 over m multiplied by m filters. That's the total computation that you need to apply per unit time. Okay. So that's a saving of a factor of m. And it makes sense because that's exactly how much you're going to be downsampling by. We're going to downsample by a factor of m. We shouldn't compute that many computations, right? That's that many. The beauty about this is highly parallelizable too, right? Because you compute all of these in parallel. So you can do that distributed if you wanted to. and do all sorts of other things, right? Yeah. The what? The max, yes, that's right. That's right.
So in that case, we're just like one sample, then
One sample, so you're right. So you downsample by a factor of n after you filter. Yeah. Yeah, you could do that. If you would downsample by a factor of n afterwards, then that would be the maximum. Yeah. It depends what you wanted to downsample by, right? Afterwards, and make a filter that is equivalent, that doesn't compute the things that you shouldn't be computing. That's the whole idea. The whole idea here is kind of find a formal way of decomposing a filter such that you don't compute whatever you don't need to compute. If you open GNU Radio Companion, and then there's a built-in block that implements a polyphase filter because it's very efficient. And what it does, it filters and downsamples. Okay, so it's a polyphase filter downsample. Okay? Now think about this, for example, in a wavelet transform. What do? We filter and then downsample. Now we can, compute efficiently the wavelet transform using these polyphase filters. Right? Now what happens when you want to do the opposite way? So interpolation. Okay. What do you do when you do interpolation? You want to filter at the low rate and then upsample. Okay? So you'll get a similar situation where you can come up with a decomposition that would filter, upsample, and delay and add. Okay? Filter, upsample, delay, and add. Okay? That would be the result. Okay? Then that doesn't have to be a result of an upsampling, right? Of a expander, right? If I delay and add things, then I would have things in between. Okay? So in the upsampling case, again, you filter first with these E's, then you upsample, and then delay them, and then add them in a very similar way. You can show in the same way that I described here. You can come up with exactly the same derivation for the upsampling case. But what you want to do is you want to do the filtering on the lowest rate. That's where you save operations. Because if I upsample first and then I filter, it doesn't make sense, right? I'm computing a lot of things on zeros, which I know they're zeros. I really don't need to do any multiplications there. That's the idea. So don't compute whatever you don't have to. This comes very often. For example, DFT, right? If you wanted to compute the FFT, you already computed a lot of stuff. Why compute over and over it again? Use other calculations to save you time. So decompose your operation into sparse matrices. Here, in some way, we're doing a similar thing. Okay, we're ending up with a smaller matrix, right? So you could have done like a whole matrix that does the convolution, then a matrix that does the decimation, or you can just multiply, combine them together into something that is smaller. Okay, so this is, again, the same thing of doing things very efficiently. All right? It's exciting. Next time, we're going to talk about multi-rate processing in the case where you are going to filter into sub-bands and then downsample, because once you filter something into a narrow band, you can downsample it. And then do operation in this lower rate, or maybe a channel of lower rate operations, and then combine them back into a signal. Okay, let's say I wanted to do different operation and different bands of frequency. I can do bandpass filters, and I can then, I can do bandpass filters and then do operations and then combine them together, right? I could have done that. But if I did a bandpass filters, I might as well downsample, do the operations there on a lower rate, and then go back, instead of filtering on this high rate signal. Okay? So we're going to show you that. We're going to show you what the conditions are for the filters and the reconstruction that will give you a perfect reconstruction if you don't do anything in between. And that would lead, of course, to the relationship between a wavelet transform, again, and its inverse wavelet transform that reconstructs it. You're going to see this relationship back. Okay? So hopefully we'll close kind of a loop when we do this. Okay? So that will be next week. All right? Have a nice weekend.